Everyone, welcome to AgriVision4U. In this video, we are going to discuss the solution for XCE, that is Thermodynamics, for GATE 2022. So let's start with the first question. The first question is based on diesel cycle. It says, Hamara air standard diesel cycle consists of 4 processes, that is isentropic compression 1 to 2, and then constant pressure heat addition. Then हम लोगों का isentropic expansion and constant volume heat rejection. Fine, this is the basic diesel cycle. Fine, T4 is the temperature attained at the end of the isentropic expansion before the constant volume heat rejection. Okay, now the constant volume heat rejection process is replaced by a constant pressure heat rejection. Okay, that is the difference. In the air standard diesel cycle, we have constant volume heat rejection, but we're replacing it by constant pressure heat rejection, such that TA4 is the temperature reached at the end of the isentropic expansion. The state point 1 remains the same. Okay, okay. So for this, let's just draw the PV diagram first. So first process is constant pressure, isentropic compression. So isentropic compression हो गया हमारा 1 to 2, then it is constant pressure heat addition, then isentropic expansion, and then हमारा आ जाएगा heat rejection, constant pressure heat rejection, right? So this is the standard cycle. Now we need to change it, modify it according to the question. But before that, let's just draw the TS diagram because we have to deal in terms of the temperature. So for the TS diagram, हमारा isentropic compression, constant volume heat, constant pressure heat addition, then isentropic expansion and constant volume heat rejection. Now, slope of this constant volume line is greater as compared to constant pressure line in a TS diagram. So we have to keep this in mind. 1, 2, 3, and 4. Now, for the modification, I'll be changing the color. Okay. We are replacing this 4 to 1, that is the heat rejection process. We are replacing this constant volume heat rejection process by constant pressure heat rejection. And we have to change the 0.4, not 0.1. Point state or 0.1 remains the same. So it will be like constant pressure heat rejection. अगर हम लोग इसको replace करेंगे, it will be like this. So this will be 4A. Fine. Because we have to continue this isentropic expansion till we achieve 4A point, till we achieve the temperature at 4A, and then we move to 1 at a constant pressure heat rejection process. Fine. Similarly, यहाँ पे हमारे पास 4 था, then we have to draw a constant pressure line. Now, this is a constant volume line, and the slope of constant pressure line is lesser as compared to that. So if we want to achieve the state point, the slope हम लोगों का for a line which has lesser slope, उसकी value यहाँ से आएगी. So we extend this point. And we'll be getting here. Okay. So this will be the, just erase this constant pressure line, constant volume line हमारी ये थी. And now this red line is the constant pressure line. Fine. So the slope is lesser. We have to keep this in mind. So this is the 4A point. This earlier point was 4 and this is 4A point. So we know the temperature scale है ये हमारा y-axis and T4A is lesser as compared to T4. So the option A would be the right answer. That means T4A is lesser than T4. So this is the right answer. Now, moving ahead. Moving ahead, we have this question, number 2, that is gas in a cylinder piston device expands from state 1 to state 2. The conditions are given P1, V1, T1, and P2, V2, and T2. The expansion process is a polytropic process. PV to the power n is equals to constant, where n is not equals to 1. If n will be equals to 1, then that will be an isothermal condition, right? So it's given that n is not equals to 1, and assuming that the ideal gas behavior, expression for work done by the system. Okay, so they are asking, हम लोगों को derive करना पड़ेगा the expression for a polytropic process that is done by the system. Now, it's given that PV to the power n is equals to constant. And we know the work done for a closed system, we are assuming it's an ideal case. Then in that case, हमारा work done would be equal to integration PdV, right? So what we can do over here, we can replace this P by C by Vn. Okay. First of all, let's just write it like this: P1 V1 whole to the power n is equals to P2 V2 whole to the power n, right? And that will be equals to constant. So what I'm going to do, I'll be using this expression and putting it over here. So work done would be equals to integration. So this P would be replaced by this expression. It will be C by V to the power n into dV. And C हम लोग यहाँ से replace कर सकते हैं in terms of P1 V1. It will be P1 V1 whole to the power n divided by V to the power n into dV integration, right? So P1 V1 तो हमारा constant ही है, so we can take this out. It will be like this, and dV divided by V to the power n. Integrating this equation, we'll be getting P1 V1 whole to the power n, right? And V to the power 1 minus n yeah, sorry, it will be minus n plus 1, right? So it will be like this, and then we have to replace it by minus n plus 1 over here itself, and then हम लोग इसको integrate कर देंगे from V1 to V2. On doing this, on rearranging, you will be getting work done will be equal to, we can remove this V to the power minus n, and हम लोग यहाँ से इसको कर सकते हैं P1 V1 whole to the power n, and it will be V2 1 minus n divided by, यहाँ पे 1 minus n लिख सकते हैं हम लोग, minus V1 whole to the power 1 by n. So we can replace it by we'll be using this formula again and rearrange it and write it like this: P1 V1 whole to the power n, V2 1 minus n minus, यहाँ से आपका P1 1 minus n और ये cancel out हो जाएगा, so we'll be getting P1 V1 divided by 1 minus n. Now using this formula, we can write कि P1 V1 whole to the power n is equals to P2 V2 to the power n. So यहाँ पे हमारा V2 to the power 1 minus n भी available है, so we can use this expression along with this to get P2 V2 minus P1 V1 divided by 1 minus n. So that means option B would be the right answer. That means work done in a cylinder piston device. When we are talking about a polytropic process, it will be equal to P2 V2 minus P1 V1 divided by 1 minus n. Moving ahead, we'll be talking about question number 3. The question number 3 is based on heat engine cycles. So let's just first read the question and decide. The temperature of the working fluid in a real heat engine cycle changes during heat addition and heat rejection process. The maximum and minimum temperatures of cycles are T max and T minimum respectively. If NC is the thermal efficiency of a Carnot engine operating between these two temperature limits, then the thermal efficiency of the real heat engine. Okay, fine. So we know the second law. The extensions of the second law says for any two cycles, if one is Carnot cycle and the other one is the real cycle, efficiency of Carnot cycle would be maximum as compared to the efficiency of any other cycle that are working between the same temperature limits, right? Because हमारा Carnot cycle में there is no losses, so therefore we talk about the efficiency is maximum in case of Carnot cycle when compared to any other cycle that is working between the same temperature limits. So the option would be NC is greater than efficiency for a real cycle. So option B would be the right answer. Yeah, option B would be the right answer because हमारा Carnot cycle की efficiency हमेशा सबसे ज़्यादा होती है. Coming to the next question, question number 4. It suggests कि हमारा rigid vessel दे रखा है, its volume is given and its mass is given. This saturated vapor liquid mixture, we are given with the volume and the mass, okay, at the particular temperature, and we need to find out the specific enthalpy of this mixture. So specific enthalpy of the mixture would be H, right? And for any two-phase liquid or a liquid vapor mixture, the enthalpy का formula would be HF plus X times of HFG, right? And this will be equal to HF plus X times of Hg minus HF. We know HF at 150 kilopascal, we know Hg, but we don't know about the quality, that is the dryness fraction. We have no idea about it. So we can use this volume wala data in order to get this. So the specific volume hamara would be equal to specific volume of the liquid phase plus X times of VFG, right? So now this total specific volume would be 1.2 divided by 8, right? Because mass up volume de rakha hai and mass de rakha hai, so we can divide it and get, and Vf is already given, that is 0.001053 plus X into Vg minus Vf, that is 1.1594 minus ka 0.001053. Now we will be calculating this. I've already calculated, and the answer would be, or the value of X that you will be getting from here would be 0.128. Right, so we have got the dryness fraction, which is equal to 0.128. Now in order to get the specific enthalpy of the mixture, we can use this expression that we have already written, and this HF is that is given 467.13 plus ka X that we have found 128 multiplied by 2693.1 minus ka 467.13, and on solving this equation we'll be getting 752.05. Okay, and the unit will be kgs per kilojoules. They are asking in kgs per kilojoules, and the unit is also the same, so it will be approximately this answer. Fine. Now coming to question number 5. Question number 5 says ki an air is in a closed system undergoes a thermodynamic process from initial temperature of 300 Kelvin to a final temperature of 400 Kelvin. The specific heat of the air at constant volume CV linearly varies with temperature as given. Now we have to find out the specific internal energy for the system. Now the specific internal energy, that means ki kgs का कोई मतलब नहीं है, that means we are not considering the mass over here, so it will be CV dt, right? Integration CV dt. If it would have asked about specific enthalpy, then it will be CP dt, right? But यहाँ पे हम लोगों का specific internal energy की बात हो रही है, so we need constant volume का specific heat of the air, which is already given. So all you need to do is integrate it from here. So with respect to temperature, from the lower limit 300 to the upper limit 400, CV की value will be putting over here, that is 0.7 plus 0.27 into 10 to the power minus 3 into T into dt, right? So let's just integrate it. On integration, we'll be getting 0.7 into T plus ka 0.27 divided by 10 to the power 3 into T square by 2. From 300 to 400, on putting the limits, we'll be getting 0.7, 400 minus 300 plus ka 0.27 divided by 2 into 10 to the power 3, and it will be 16,000 minus का this thing. ठीक है, हम लोग ने square कर दिया, and on solving this we'll be getting this value of specific internal energy, that will be approximately 79.45 kilojoules per kg. ठीक है, yeah, this will be the answer for this question. It's just the matter of integration. बस हमें ये पता होना चाहिए कि the specific internal energy is equal to CV dt, and we have to integrate it. That's it. Coming to question number 6. Question number 6 is a vertical cylinder piston device contains a fixed mass of gas in equilibrium. The cross-sectional area of the piston is given. For 150 kilopascal pressure in the cylinder, the mass of the piston is. Okay, so we need to find out the mass of the piston, and the pressure of the gas in the cylinder is this. The atmospheric pressure is given to be 100 kilopascal, and the specific acceleration due to gravity is this. Okay, fine. So the total pressure on the gas is 150 kilopascal. Fine. So first, let's just draw the piston cylinder arrangement. Here we have the piston and the cylinder. It says the total. Here we have the gas filled inside this. So it suggests the total pressure in the gas is 150 kilopascal. Okay, and the atmospheric pressure is 100 kPa. The rest of the pressure would be because of this piston, right? So the pressure की वजह से piston we are denoting by P piston. That means the total pressure on the gas would be equal to atmospheric pressure plus the pressure due to the piston. So it is 150 that will be equal to 100 plus P piston. Right? Okay. Now, the pressure that piston would apply would be equal to the mass, matlab would be responsible according because of its mass, right? So pressure is equal to force by area, and force is because of the mass, that is the gravitational force. So it will be mg divided by area. Okay, we'll replace it over here. On rearranging, we'll be getting 150 minus 100 will be equal to mass of the piston multiplied by acceleration due to gravity divided by area, that is 0.05. On solving, mass will be equal to 50 into 0.05 divided by 9.81, and this will be equal to 254.84 kgs. Right? It's a very simple question. You just need to put the formula into it, and we'll be getting the answer for it. Fine. Coming to question number 7. Question number 7 is based on Rankine cycle. Okay, let's just read the question first. A steam power plant operates on Rankine cycle. At certain operating condition of the plant, there is a reduction of 20% net work output as compared to 100% capacity. This reduction will cause the specific steam consumption, that is kgs per kilojoules, to increase by this. Take it. Now, first we'll talk about the reduction in net work output, right? And then we'll compare it by 100% capacity. Okay. So the reduction is 20%. So I'll be writing reduction in net work output is equals to 20%. Let's just suppose हम लोगों का initial work output was the net work output. Initially, it was 100%. It's already given, right? And then reduction हमने 20% कर दिया. So now the new net work output would be output would be equal to 100 minus 20, that is 80%, which we can write as 0.8. We can write it as 0.2 and we can assume it to be 1. Fine. Now, we know the formula between the net work output and the specific steam consumption, that is net work will be equal to the net specific steam consumption, right? Where specific steam consumption I have denoted by SSC. So the new network consumption is 0.8. So we can find out the new specific steam consumption, and the new specific steam consumption would be equal to 1 by 0.8. It is 1 by 1.25, right? So if we multiply it by 100, it would be 125%. Now, initially when we had 100% work output, then in that case, आपका जो specific steam consumption would have been, that would also have been 100%. But यहाँ पे the new specific steam consumption is 125%. So we'll be subtracting 100% from this, and we'll be getting 25%. That means the reduction in 20% of the network output would cause the specific steam consumption to increase by 20%. Yeah. Let's just move to the next question. It is a Carnot heat pump extracts heat from the environment at 250 Kelvin, okay, and supplies 3 kilowatts of heat to a room which is maintained at a constant temperature TH. Okay. The pump requires a power input of 1 kilowatt for this operation. Then the temperature TH. Okay, fine. So we need to find out the temperature TH. Here we have the work, and here we have the environment, that is TL, which is equal to 250 Kelvin. It is supplying heat of 6 kilowatt to it. So it will be QH will be equal to 6 kilowatt, and power input जो इसमें लग रहा है, that is 1 kilowatt. We are talking about Carnot heat pump. That means the ratio of heats and temperature would be constant. Fine. So let's first talk about the COP of heat pump, which will be equal to the desired effect divided by input, power input, right? Here we can express this in terms of heat as well as in terms of temperature. So desired effect would be QH divided by power input, हम लोगों का work हो जाएगा, and this will be equal to TH divided by TH minus का TL, because आप work अगर निकालोगे that will be equal to QH minus का QL. Fine. So because we are talking about Carnot heat pump, so the temperatures ka ratio and the heat ka ratio would be same. That is why I've written this expression. Now QH is already given, that is 6. W is also given, which is equal to 1. TH we have to find out, divided by TH minus ka TL. TL is 250 kelvins. So what we'll get, we just have to solve this expression, and on solving this expression, we'll get TH to be 300 Kelvin. Fine. That means the temperature of the room is 300. Question number 9, that says the general relation among the properties X, Y, and Z at any state point can be expressed by this expression. If pressure, temperature, and enthalpy are continuous functions, and Cp is given to be like this in terms of enthalpy, temperature, and pressure, and Joule-Thomson coefficient is dever H by dever P at constant temperature, then we have to find out we have to find out कि this expression, okay fine, mu दे रखा है आपको, and we have to find out this expression. ठीक है. So first we'll be rewriting this given expression in terms of pressure, temperature, and enthalpy. I'm assuming that हमारा जो है, we'll be writing for enthalpy, pressure, and temperature. So X would be replaced by enthalpy, Y would be replaced by pressure, and temperature हम लोग Z से replace कर देंगे. So this expression becomes dever H by dever P at constant temperature multiplied by dever Y, that is dever P, by dever Z, that is dever T at constant enthalpy, multiplied by dever Z, that is dever T by dever enthalpy at constant pressure, would be equal to -1. Okay. Now Cp is given that it is equal to dever H by dever T at constant pressure. That means ये हम लोग इसको replace कर सकते हैं. We need to find this expression. So this expression is written right over here, which is this, multiplied by, we are replacing it by 1 by Cp, which is equal to -1. Now mu is the throttling coefficient, that is the Joule-Thomson coefficient, and Joule-Thomson coefficient में what do we say at constant enthalpy the change in temperature is measured in terms of change in pressure. That means dever T by dever P at constant enthalpy. So this expression dever P by dever T at constant enthalpy is right over here. So we can replace it by 1 by mu. That means dever H by dever P at constant temperature would be equal to minus ka Cp into mu. Hence the answer would be minus ka Cp into mu. That means this expression is equal to minus ka mu into Cp. Okay, let's just move to question number 10. It says an air conditioning system consists of an insulated rigid mixing chamber designed to supply air at 24 degrees Celsius to a building. The mixing chamber mixes two air streams, that is a cold stream and a stream of fresh ambient air. ठीक है, first let's just say कि cold air stream के specifications क्या है, 10 degrees Celsius and MC mass flow rate. Fresh ambient air is at 30 degrees Celsius and mass flow rate is MA. ठीक है. Assume that the air to be an ideal gas with constant specific heat Cp and gamma is given, so we can find out Cv. Now neglect the change in potential energy and the kinetic energy as compared to the change in enthalpy. Under the steady state condition, the ratio of mass flow rate for the two streams. Fine, that means what we are doing, we are mixing two streams and we'll be getting, that is air stream, and this is the cold air stream. That gives total mass flow rate that is to be maintained at 24 degrees Celsius. So 24 degrees Celsius, and this total mass would be equal to mass flow rate of the air stream plus mass flow rate of the cold air stream. Cold air stream is coming at 10 degrees Celsius and this is coming at 24 degrees Celsius. Fine. So what we have to find out? We have to find out the ratio between the cold air and the fresh ambient air. So let's just apply the mass balance or the enthalpy balance over here. That is, यहाँ पे the enthalpy of the air, that will be the mass of air multiplied by Cp of air and the temperature, that is 24 degrees Celsius. 24 degrees Celsius plus 273. 24, yeah. Sorry, this is not 24, this is 30 degrees Celsius. Yeah, 30 degrees Celsius plus 273, that would be 303, plus mass of cold air into Cp of air multiplied by temperature 10 degrees Celsius. So 10 degrees Celsius would be 73 plus 10, that is 283. 283. It will be equal to mass of air plus mass of cold air multiplied by Cp into टेम्परेचर हमारा हो जाएगा, दैट इज 24 plus 273, 24 plus 273 degrees Celsius, that is 9, that is 297. We just need to rearrange it. But before that, जो हमारा constant specific heat at constant pressure, that will cancel out from the entire expression, and we have to mass flow rate of air यहाँ से अगर हम लोग इकट्ठे कर लेंगे, then it will be equal to 6 times of mass flow rate of air, and it will be equal to 297 minus का 283, that is 14 mass flow rate of C. So mass flow rate of C divided by mass flow rate of A will be equal to 3/7. That means 3/7 is the ratio between the mass flow rates of the two streams would be 3/7. Now coming to question number 11, it says an ideal gas mixture consists of 80% nitrogen and 20% oxygen on mass basis. If the total pressure is this, and then the partial pressure of N2, we have to find out the partial pressure of N2. That means हमारा जो mixture है, that is 80% nitrogen and 20% oxygen. So partial pressure we have to find out. Okay. So partial pressure would be equal to, of nitrogen would be equal to total pressure multiplied by mass fraction or the molar fraction. Molar fraction हम लोग उससे multiply करेंगे, तब जाके we'll be getting it over here. So here we have the mole fraction multiplied by total pressure would be equal to the partial pressure of N2. So we have to find out the mole fraction first. That means number of moles of N2 divided by total number of moles, that is number of moles of N2 plus number of moles of oxygen. Here it is N. Okay, fine. So यहाँ पे number of moles of N2 would be, it is 80% by mass. Okay, so it will be, let's just say 80%. Let's just say हमारा total x kgs था, तो हमारा 80% of x kg would be 0.8 x divided by N2 का molecular mass, it is 28, divided by mass of N2, that is 0.8 into x divided by 28, plus mass of oxygen, that is 20% of x, that is 0.2x divided by molecular mass, that is 32. From here we can see x हमारा cancel out हो जा रहा है. This x, let's just say it is k, otherwise we'll get confused. Yeah, we are here कि हमारा जो total K है, total mass of the air is K kgs, and out of which 80% is nitrogen and 20% is oxygen. So nitrogen would be 0.8 times of K and oxygen would be 0.2 times of K, right? So this is what I've written. The mass of nitrogen, it is 0.8 K divided by molecular mass हम लोग कर देंगे, then we'll be getting number of moles of N2. The number of moles of N2, it is 0.8 K divided by 28 plus number of moles of oxygen would be mass of N2 divided by molecular mass of oxygen, that is 0.2 K divided by 32. So on solving, we'll be getting the value of X, that is the mole fraction of N2. It will be approximately, let's just calculate it first and then I'll be writing over here. On solving, we'll be getting the value of X, that is the mole fraction of N2. It is coming to be 0.8205. Fine. So it is 0.8205. So all we need to do is we need to multiply it by total pressure and we'll be getting the partial pressure of N2, that is equals to total pressure is 300 multiplied by 0.8205 and 300 multiplied by 0.8205, it comes about 246.153. That means kPa, right? So that means the answer would be 246.15 kPa would be the partial pressure of nitrogen in this gaseous mixture. Moving ahead, we have, on the basis of ideal gas equation and van der Waals equation, the temperature of the gas at 10 megapascal and specific volume this would be respectively. अच्छा, okay, we have to find out कि ideal gas equation से हमारा temperature क्या हो रहा है and van der Waals equation से क्या हमारा temperatures निकल के आ रहे हैं when we are given with this pressure and the volume. Now, as you can see in all the options that were given, the first expression is same. That means the temperature, when we find out by the ideal gas equation, will be getting the same. So there is no need to find it out. So we'll directly switch to van der Waals equation. So the van der Waals equation for any state would be P plus A by V square multiplied by V minus P is equals to R into T, where V is the specific volume, right? So pressure हम लोगों को पता है, we have to find out the temperature. Okay, fine. So temperature find out करने के लिए we just rearrange this equation and write it again. P plus A by V square, V minus का V. Okay, so 1 by R. R is given 0.3. Pressure that is already given, it is 10 megapascal, but here we are talking about everything in kilojoules or kilopascals, so we'll convert it into kilo unit, that is kilopascal में convert कर देंगे and it will be 10,000, right? 10,000 pascal, kilopascal plus A की value is given to be 0.18 divided by specific volume, that is 0.05 का whole square, and V again 0.05 minus the V, that is 0.0014, and on solving this we'll be getting the value of temperature to be 206.4 Kelvin. That means it will be option B. Option B would be the right answer because the value is given to be 206.40 Kelvins. Fine.